All right, so here we are with Chapter 9, Section 2. We're going with series and summation notation. So we've got some notation that we'll be going over today. So we need to use this notation to evaluate the sum of a series expressed in sigma notation, which is what summation notation is. All right, so some vocabulary that we're going to get with is series, a partial sum, and also a summation notation. So I'll have each of those definitions within the video. All right, so a series is the sum of terms of a sequence. So instead of what we'd been doing previously, which was just listing them with a nice comma between, we are now going to add them. Okay, so before we had been doing sequences, and now we're doing series. And series is different than sequence just by adding a plus sign. That's it. So this is a finite series and sequence because notice it ends. Over here, we've got an infinite sequence and series because of this ... going on over here. And then this is also another finite series just with fractions. All right. So first thing that we're going to look at here is a partial sum. And a partial sum is the sum of a specified number of terms of a sequence. So we kind of just looked at that. And so this is, for instance, a partial sum because there's only 4 of them. It doesn't go on for infinity. So this is a partial sum. All right. So if we go ahead and try to add all of the even numbers, the sum of the first term of even numbers would be the sum or series with this S here. And then the fact that we're adding one term. And so that first even number is 2. If we want to do the first 2 terms, that would then take 2 and 4, because those are the first 2 even numbers. And that little 2 again indicates that you have 2 numbers. And then, of course, the sum is 6. The sum of the first 3 even numbers is 2 plus 4 plus 6, so 12. And the sum of the first 4 numbers is 2 plus 4 plus 6 plus 8, so 20. So you're always taking the previous number and then adding that next even value, at least in this sum. So partial sums always have this number down here by the S indicating how many terms you're going to add together. All right. So then we have this scary summation notation. It uses the Greek letter sigma, and it's a capital sigma. So it's not the lowercase sigma, which is like a cursive O. Okay, so this is your capital sigma, and we need to denote the sum of a sequence. It denotes the sum of a sequence defined by a rule, which is just a function or a guide. So if we take a look at what is going to happen, you're going to have your sigma each time, and then right here is going to be your explicit formula for your sequence. Okay, we like to call it a sub k in this case because we're going to be using k's instead of n's. N's was what we used in a sequence, but in a series, we're now going to be using k's. All right. So you're going to evaluate this explicit formula for the values from 1, because it's always starting at the first value of 1, and then ending at, in this case, 5, or whatever the top number is. So let's say that you have it listed from 0 to 20. That means that you're going to have 20 of those numbers that you're going to have to add, because the sigma here, together based on whatever this rule is. So kind of a lot to go on, but we're going to use this notation here. So we're going to write a series in summation notation. So we're going to write it in this type of notation. And the first thing that we're going to do is write a rule for the kth term of the sequence, and then we're going to write the notation. So all we need to do is first find out how you get from 4 to 8 to 12 to 16 to 20 with a sub k formula. So our rule is an equation that we're going to call a sub k. And so all we need to do is figure out what do I do, for instance, to the number 1 to get 4, because that's how you get from our x value, if you will, to our y value. So how do we get from 1 to 4, or 2 to 8, or 3 to 12, or 4 to 16, or 5 to 20? And so hopefully you can realize that that means that you're just going to take the k value and each time multiply by 4, right? 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12, 4 times 4. So that means that you're going to take the k value and multiply by 4. So that's our rule. So now that we have our rule, we're going to write our notation. So our notation says we're adding each of these. So that's where the sigma comes in. I usually just kind of make it like a sideways capital M, little marks here. So right here in this space is going to go our rule. So we're going to write 4k right there. And then notice that we did start at the number 1. So we're going to say that our start is at 1. And our end is at, well, how many terms do we have? 5. Okay, so 4k is the rule. This is our starting value, and this is our ending value. All right, so that is using summation notation. Hopefully it's not as difficult as you once thought. All right. So what happens is there may be a sequence where all of a sudden, instead of saying 4 plus 8 plus 12 plus, instead of having all pluses, perhaps you're going to have a first term that's positive, but then a second term that's negative, and then a first term that's or a third term that's positive, and then negative. So for instance, if we looked at this one, it would be 4 minus 8 plus 12 minus 16 plus 20. So the idea would be that we are going to alternate the negatives. If the first term, if you are alternating signs, if the first term is positive, you're going to have to put this out front. If the first term is negative and then alternates, you're going to have to put this out front. So we put it out front next to the rule. So we would do a rule like we did here, but then just in general without focusing on the negative, and then use one of these depending on what negative is happening. All right. So of course, this next example uses this alternate idea, okay? So first we'll find a rule for the kth term of the sequence, and then we'll kind of identify this negative positive thing. So we're going to start with a rule, which we're calling a sub k. And so we need to say that that's not an R, that's a K. Okay. So our first term is going to get us a 1. Our second term gets us 1/4. Third term is 1/3. Fourth term is 1/9. Then we have 1/16, 1/25, and 1/36. So hopefully you can realize, especially if we take the time to rewrite this as 1/1, this is actually 1 squared. Down here, the denominator is k squared. Over here, it's k squared to get 9, 4 squared is 16, 5 squared is 25, and so on. So in that case, we're saying you need to take 1 over the k value that we will square. Okay, then we need to note, because there's alternating signs, right? You see that there's a minus, plus, minus, plus, minus, plus. So is the first term positive or the first term negative? So back to our example, the first term is negative. So first term negative means that I need to include this set of symbols with my rule. So my new rule with alternating signs, and my first term is negative, means that I'm going to insert -1 in parentheses to the k. And then that is going to be multiplied by the original idea of 1 over k squared. So this is the entire rule to get each of these terms being negative then positive. All right, so that is what we're going to put in our summation notation as the rule right here. So we're going to put -1 to the k, and then we'll multiply by 1 over k squared. All right, then we have to put the things on the bottom and the top. And so remember that this is going to be always k equals 1. We're plugging in a 1 for the first term. And then in this case, we're going until 6 terms exist. So that is our notation. All right. Okay, so now what's going to happen is they want you to expand the series. They want you to write each of the pieces and then take all those 6 pieces and add them up. Okay. So it probably works out best if we make a table of our k's and then our a sub k's. And so it looks like we're going to start at 1 and go till 6. So 2, 3. And then what we're going to do is plug in a 1 to this equation, and that's going to be our y value. So 1 squared minus 10. Oh, I like how I put an s for squared instead of a little 2. Okay. So 1 squared minus 10 is going to be 1 minus 10, which is negative 9. So negative 9 is our first term. Our second term is going to come from plugging in a 2 to this equation. So 2 squared minus 10, so 4 minus 10, which is negative 6. Then the next one comes from plugging in a 3, so we're going to get 3 squared minus 10, so 9 minus 10, which is negative 1. And then we're plugging in a 4, and 4 squared is 16, minus 10 leaves us with a 6. 5 squared is 25, minus 10 leaves you with 15. And 6 squared is 36, minus 10 leaves you with 26. All right, so that's all we do is plug in each of those. So that's your expanded part. Okay, but now we need to actually evaluate. So if we're going to evaluate, that means that we actually need to add these numbers. So we're going to take negative 9 plus negative 6 plus negative 1 plus 6 plus 15 plus 26. And so we're actually going to get the digit that equals that summation notation. So negative 9 minus 6 minus 1 plus 6 plus 15 plus 26. So taking a look at this, apparently 31 is what happens when we evaluate it, and when we expand it, that's each of these numbers, which we wrote here as well. All right, so again, we knew our terms went from 1 to 6 because of those numbers. We knew that these were our terms because we plugged in the k value to each of them and got the new number. And then to evaluate, we had our addition of all of them. All right. So we also have a few formulas that are going to be happening. So you will have access to your formula sheet here. Notice that we have the summation notation, which we kind of talked about today. So talking about how k goes from 1 to however many numbers you have of the form. This is the next one that we're going to talk about, and then we'll also go over these two as well. So this whole set here is from chapter 9, section 2. All right. So this first one is saying, what if you had the sum of whatever number to whatever number of a constant number, like in this case 3 or 26 or whatever. All it's saying is that you are going to take that 26 or that 3 or whatever that constant number is and multiply it by the number that's on top here. As long as this is 1, we just multiply it by the number of terms that there are. Because technically, if you have the sum of the number 3, you're going to add 3 to itself as many times as it says here. So 3 times 5 would get you 15. Or, of course, you can sit there and do 3 plus 3 plus 3 plus 3, but hey, that seems unnecessary. Of course, because we want to do it for all options, they are saying that you're going to do it for n times c, which just means this number up here times this number over here. Again, as long as everything starts at 1. So, taking a look at an example here, looking at a few more key terms. A linear series is a counting series such as the sum of the first 10 natural numbers. So if we examine the terms and how they are arranged here, this is saying that k is starting at 1 and going till 10. So we're going to take 1 plus 2 plus 3 plus 4 all the way to 10. And if you take the time to kind of rearrange them so that they make sense, we have 1 plus 10, which is going to make 11. But then 2 plus 9 also makes 11. 3 plus 8 is 11. 4 plus 7 is 11. And 5 plus 6 is 11. So technically, we end up taking 11 5 times. And if we look at what we have here, 11 is actually this number plus 1. And 5 is actually this number divided by 2. So when we look at summing numbers between 1 and 10, or each number in a sequence, we're going to look at this formula. So we're going to take n, which is this top number. In the previous case, that would have been 10, and then times 11, but then divided by 2. This other one here talks about when k is squared. So if we say that we're going to take 1 plus 4, which is 2 squared, plus 9, plus 16, plus 25, so those perfect square values. That's when we're going to use this one. And again, this n value is up here. All right, so these are some formulas, again, that you are going to have on a formula sheet. So here we go with this one. So the only other problem is that sometimes they won't start at 1. They'll start at a different number. And so you have to be very careful that what looks like, in this case, 5 terms, because you're starting at 5 and ending at 10, you actually have term 5, 6, 7, 8, 9, and 10, which is 6 terms. So be careful when you're doing this for checking your answer, because you're going to think that you needed to add 5 numbers and you'll have 6, and then you'll think you're doing it wrong. So instead, just say, okay, remember that this isn't 8 times 5, it's 8 times 6, because there's 6 times that you will add it in there. Usually I just count them out in my head. All right. So we're going to do our formula, but then we're also going to just expand and see if it works. This one is usually more time consuming. All right, especially when your ending value is very large, which on the test there will be one that has like a 50 in it. Okay, and you're not going to sit there and add 50 numbers. You're instead going to throw it in the formula. Okay, so in this case, notice that we are basically taking the number 6 and we're going to add it a few times. It looks like we're going to add it 6 times, but we're actually going to add it 7 times. So we're going to use the summation formula to get there. And you'll notice that this is a sigma. It doesn't necessarily start at 1, but it does have just a value. So we're going to take that value and multiply by the number of times that we're going to have that term. So in that case, it is not just n times c, okay, where n is 10 and c is 6. We're not using 10 because n is actually the number of terms. And in this case, our number of terms starts at 4 and goes till 10. And so if we look at the number of terms themselves, that's 4, 5, the 6th term, 7th term, 8th term, 9th term, and 10th term, which is actually 7 terms. So we're going to be doing 7 times 6, and that's going to be 42. All right, if we did the expanding piece, we would have come up with the fact that our k value is 4, but then it's 5 and 6. And that our a sub k starts with 6 that we will add to 6, and then continuing on. And so 6 plus 6, 7 times is going to add to be 42. So again, either way, we could take the time to list them out, which when it's a kind of more difficult sequence, it's a little bit easier to do or more helpful. But in this case, just 7 times 6. All right. The next one says that we're going to evaluate just the formula K. And so if we look at the formula sheet, the formula says that you're going to take this n value as long as it starts at 1, which it does, multiply by the n value plus 1, and divide by 2. So our formula says n times n plus 1 divided by 2. And in this case, we've decided that n is 8. So we're going to take 8 and plug it in. And so we'll have 8 times 9. And that's going to get you 36. Yeah. Okay, so formula. However, the expanding and evaluating says that we're going to take our term number, which in this case is 1 through 8, and plug it into the formula and list it out. So if I plug in a 1 for k right here, we get 1, which will add to 2, and 3, and 4, 5, 6, 7, and 8. So we're actually going to add those together. And so just to double check, we've got 1 through 8 added together, and that is also 36. So remember that if you are completely lost with your summation notation, you can just plug in the terms that you have and add them all up. But of course, once you get into a very large n value, that's going to be not very helpful. All right, and then this one here says to use a graphing calculator, but that is not actually the second method. It's just to expand it. So not really sure why it says that. All right. So first thing we're going to do here is use the summation formula. So again, notice this says k squared. And so our k squared tells us that the formula is this one, as long as it starts at 1, which it does. So our n value in this case is 12. So our formula is going to be n times n plus 1 times 2n plus 1, and all of that divided by 6. And we've decided that our n value is 12. So we'll do 12 times 12 plus 1 times, what is this? 2 times 12 is 24. So 2 times 12 plus 1. So, and then divided by 6. So that's going to be 12 times 13 times 25. All of that divided by 6. And so again, instead of adding up 12 terms, we're just going to do 12 times 13 times 25. All that divided by 6, and we get 650. So in this next one, we're going to go ahead and expand for these 12 terms. I guess I'm going to probably have to write smaller. So here's our k term, and then our a sub k, or what happens as the result of squaring k. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared 49, 8 squared 64, 9 squared 81, 10 squared is 100, 11 squared is 121, and then 12 squared is 144. So now we're going to take the time to add up each of these numbers. And so 1 plus 4 plus 9. And I missed a 0 in there. All right, so let's double check. 1, 4, 9, 16, 81. Okay. So all of those is 650. And so you can kind of see how accidentally mistyping one of these is going to be a lot more significant than just multiplying these 3 digits here rather than adding all 12 of them. So definitely an easier method. All right, so hopefully we now know a little bit more about series and summation notation and evaluating our sums of series in this fancy sigma notation. So you will now have an assignment for this.